Hi, I'm Mr. Miller, and this is a lesson on equations and graphs of trigonometric functions. So in the first example, we're looking to solve 4 sine squared x minus 3 equals 0 on 0 to 2 pi, and then for all x. So let's take a look at how this can be done. So I'm just going to copy out the equation here, and then I'm going to try to isolate the sine x. So I'm going to add 3 to both sides. Then I'm going to divide both sides by 4. And then I'm going to take the positive and negative square root of both sides. And so there are a few different ways I can solve. One of the ways I can do it is graphically. And so if I graph this on 0 to 2 pi, and I graph it y going from -1 to 1, this is what it would look like. So my first graph is y equals sine x. My second graph is positive root 3 over 2. And my third graph is negative root 3 over 2. And so what you'll notice about this is we've got the sine x intersects with root 3 over 2 in 2 places here. And sine x intersects with negative root 3 over 2 in 2 places down here. So if I find the points of intersection, the roots of the equation are the x-coordinates of the points of intersection. And so if you're doing a graphical solution, it's important that you identify how the graph relates to your solution of the equation. So it's the x-coordinates of these points of intersection. So for instance, this point here is the point pi over 3 and root 3 over 2. Well, the root 3 over 2 is not the solution of the equation. It's the y-coordinate, right? The x-coordinate is the one that's actually the root of the equation. So it's x equals pi over 3. And then at x equals 2 pi over 3, we also get root 3 over 2 for y. And so that's the second x-coordinate that gives you intersection of the sine x with root 3 over 2. And then the last two here come from so at x equals 4 pi over 3, this gives you negative root 3 over 2 for sine x. And at x equals 5 pi over 3, we get negative root 3 over 2 for sine x. So those are the 4 roots of the equation, and they are the 4 points of intersection on the graph. Now, you don't have to do the solution graphically. Here's a non-graphical solution. What I would do is separate it into sine x can be root 3 over 2 or sine x can be negative root 3 over 2. And I would draw out the two solutions in standard position. So here's x1 and x2. And you can recognize from special triangles if you've got sine x is root 3 over 2. So just think of x as the angle. And if sine of an angle is root 3 over 2, that's like y over r. Root 3 over 2. So it's a 1, 2, root 3 triangle. This angle is 60 degrees or pi over 3. And the other one has the same reference angle of pi over 3, and it's 2 pi over 3. Or pi minus pi over 3 gives you 2 pi over 3. The other part of the solution comes from when sine x is negative, root 3 over 2. So again, y over r, negative root 3 over 2. Negative root 3 over 2 this way and negative root 3 over 2 that way. So we get two angles. One I'm calling x3, the other one I'm calling x4. You'll notice they all have the same 60 degree or pi over 3 reference angle. And so it's pi plus pi over 3, which is 4 pi over 3, or 2 pi minus pi over 3, that's 5 pi over 3. So those are the same four roots of the equation that we got graphically. Now, to get the solution for all x, you take each one of those individually and you add multiples of 2 pi and specify that the multiples have to be integer multiples of 2 pi. Let's take a look at this example number 2. So we've got, we want to solve tan 2x equals 3 for all x. So first off, let me just draw this. You can have a tangent which is 3, having a y over x of 3 over 1. So here's the reference angle. Here's the principal angle for which the tangent is 3 over 1. And of course, negative 3 over negative 1 also gives you 3. And so this angle, which is 180 degrees different from the first, or it's the first solution plus pi. And if we add pi, it will go to the next root, and add pi, it goes to the next root. So adding multiples of pi from this very first one is all we need to do to solve for all x. So we take the inverse tangent of 3 to get that angle, and then we add multiples of pi. And if we divide both sides of this equation by 2, then we get x equals about 0.62 plus n pi over 2, where n is an integer. So here is a very typical pre-calculus 12 trig application question. It's the Ferris wheel question. So here we've got a Ferris wheel that does 1 revolution in 50 seconds. Passengers start at a height 1.5 meters above the ground, and the radius of the Ferris wheel is 6 meters. We want to write a function in the form h of t is a sine b t minus c plus d that will model the passenger's height as a function of time. So let's just sketch this out. Height versus time is going to look like this. So 50 seconds, I'm going to say that's 1 cycle. So I'm going to break that into 4 parts, which will make it easier to get sort of important points on the graph. I know that passengers start at a height 1.5 meters above the ground, so I'm going to mark that off as the lowest point on the graph. I know that the Ferris wheel is 6 meters in radius, so you can see the Ferris wheel that I've drawn here, which would put the mid height on the ride 7.5 meters above the ground. And if you add another 6 meters, that takes you to 13.5 meters above the ground for your highest height on the ride. And now here are the significant points that I would use. So it says that the passengers start at a height 1.5 meters above the ground, which means they're starting here. And I know that in 50 seconds, we're going to be back to where we started. Halfway through the ride, 25 seconds into it, we're going to be at the maximum point. And if we find the midpoint between those two, 12.5 seconds into the ride, we're going to be at the middle height on the ride. And again, 37.5 seconds into it, we're going to be at that 7.5 meter mark. So if I connect those points together, it's at least a reasonably good representation of the height versus time graph. And so now I can write this height function as a sine function, and just need to figure out what the a, b, c, and d values are. So I know, first of all, that it's a plus 7.5 because that is the vertical displacement. I know that the amplitude is 6, which also corresponds to the radius of the Ferris wheel. I know that sine graph usually starts at this point and goes up from there. So this point has been shifted to the right, 12.5. So that's why t has been replaced with t minus 12.5. And I've got 2 pi over 50. So this is in standardized form, 2 pi over the period. Period is 50. Now you can reduce that to pi over 25 if you want, but you can also leave it as 2 pi over 50. So this is the height function for this graph. Now, if you wanted to know the height of a passenger 45 seconds into it, you could substitute into that equation and calculate. You should find you get about 2.65 meters. And now the next question is, for how long in one rotation are passengers over 10 meters in the air? So you would graph h equals 10, and then find those 2 points of intersection on the one cycle. And you can also get that from finding the solution of this equation, and you'd find that it happens at 15.92 seconds. So 15.92 seconds is where the height is 10 meters. And also at 34.08 seconds is the other place where the height matches with 10 meters. Now the question is, for how long in one rotation are passengers over 10 meters in the air? And so it's between these two times that they are above 10 meters in the air. So we have to subtract those two times to find the amount of time that the passengers are above 10 meters in the air. So when you do the subtraction, you should find it's about 18.16 seconds per rotation. And final question here, we're looking at data for the average daily high temperatures for each month in Victoria. Of course, month number 1 corresponds to January and month number 12 corresponds to December. So if we take this data and we graph it, this is what it looks like. So I can see the low and high temperatures. The low temperature is 6 degrees Celsius, high temperature is 22 degrees Celsius. And so if I find the average of those two, right, 22 plus 6 is 28, divided by 2 is 14. That's going to be the middle line of this graph. And so I know also that there are 12 months involved here. So I'm going to go from 1 to 12, and I'm going to extend it to 13 because I know that the 12 months in a year, that is the cycle. And so now what I'm going to do is I'm going to start from month number 1, temperature is 6 degrees. Month number 13, which would be like January of the next year, we're going to be back down to the same temperature. And I'm going to go 6 months into it. I'm going to be at the maximum temperature, which is 22 degrees Celsius. And of course, halfway between month 1 and month 7, we'd have month number 4 would be at 14 degrees Celsius, approximately. And likewise, between month 7 and month 13, month number 10, we should be at 14 degrees Celsius again. And if I connect all those points together, we get a nice smooth curve. And this is the temperature function as a function of the month M. And so now I'm just going to specify the A, B, C, and D values that give us this cosine function. So first of all, I know it's plus 14 because that's the vertical displacement. I know the amplitude is 8 because 22 is 8 degrees Celsius above 14, and 6 degrees Celsius is 8 degrees below 14 degrees Celsius. So we've got a minus 7 here because cosine normally starts at its maximum value. And so there's a shift to the right 7 units. So replace m with an m minus 7. And finally, we go 2 pi over the period, which is 12. And again, you can reduce that to pi over 6 if you want, or just leave it as 2 pi over 12. And that is the function. And then the last question here is, what is the average daily high temperature in November? Well, that's month number 11. So if we evaluate this function at month 11, we would find that this calculates to 10 degrees Celsius. Now, in the table, we've got the temperature in November is 9 degrees Celsius. So the mathematical model here is a pretty close representation of that. So that completes this lesson on equations and graphs of trigonometric functions. Hope that all makes sense for you, and thanks for watching. Have a great day. Bye.